So good afternoon to all the respected professors, instructors, fellow speakers, and participants. This is Shonajuri Moitra. I am currently a second year undergraduate student of computer science engineering in Heritage Institute of Technology, and I have just completed my foundation in IIT Madras. So today I'm going to give a presentation on the topic, an introduction to problems related to rational points on conic sections and elliptic curves. So before diving right into conic sections and elliptic curves, let us talk about polynomials in single variable, any n-degree polynomial in single variable, right? And how we can find out rational roots of those polynomials. So René Descartes, he gave a theorem called the rational root theorem, which can be used to find out the rational roots for any n-degree polynomial in one variable. So here we can see that fx equal to an x to the power n plus an minus 1 x to the power n minus 1 and so on. This is a polynomial of n degree in one variable, right? And we have to note here that ai belongs to integers. It's okay if we say that ai belongs to rational numbers too, because when we will be finding rational roots of a polynomial, right, we will be equating it with 0. So if an minus 1, I mean ai in general are rational, we can always take the LCM, right? And then these will all be integers and we will be cross multiplying the LCM with 0. So it won't make a difference. The rational root theorem basically states that if p by q is the rational root of fx, then p divides a naught, that is the constant term, and q divides an, that is the leading coefficients. So we would be getting a few fractions, and then we can put those fractions in place of x and check if they are indeed the rational roots. We can check if for those values of x we are getting 0 as the answer. Now, it's not necessary that all the fractions that we'll be getting by this theorem would be the rational roots, but it is for sure that if there is a rational root of this polynomial, it would exist from that set of fractions that we got by the rational root theorem. So this is all about how we can find rational roots of polynomials in one variable. Now let us talk about polynomials in two variables. The simplest polynomial in two variables is a linear polynomial, right? A linear bivariate polynomial. Bivariate means two variables. Now, if you see this geometrically, ax plus by plus c equal to 0, this is the equation of a straight line. We have to again note here that a, b, c, all of these belong to rational numbers. So the coefficients are always rational, whatever equations we would be taking in this presentation. Now finding rational roots of this polynomial, this linear polynomial is pretty simple, right? We can trivially see that for any rational value of x, we will get a corresponding rational value of y. Given a, b, and c, if we take rational coefficients a, b, and c, anything, say 3, 2, 5, anything, any random rational values, if we put any rational value in x, we will get a rational value for y and vice versa, right? So we can say that this equation will have infinite rational roots, or a rational line will always have infinite rational points on it. So it's very simple, it's pretty easy there. But when we move 1 degree higher, that is when we go to quadratic bivariate polynomials, we can also show that there are infinite rational roots or 0 rational roots, but the calculations are a little bit rigorous. So when we deal with rational roots of any curves, we basically deal with two questions. One is existence of rational roots, that whether rational roots exist or not. And the second is generation of other rational roots. Like you might have noticed that I said that for quadratic polynomials, there will either be 0 rational roots or there can be infinite rational roots. So the second question deals with how we can find those infinite rational roots, right? In this talk, we will basically deal with this point, the second point, and we will try and prove it. Now, there is a theorem called the Legendre theorem, as you can see here. It tells us about the existence of rational root on conics. Okay, quadratic polynomials in two variables, we can call it conics. If fxy is a quadratic polynomial in xy with rational coefficient, then we can say that the set of all rational points, that is xy, is either empty or in one-to-one correspondence with rational points on any rational line. Now it's basically the same thing that I stated previously, that it's either empty or it's infinite, because we already showed that number of rational points on a rational line will be infinite. So let us try to understand the proof. So here I have taken a conic x squared plus y squared equal to 1, which is the equation of a circle, and we have taken a random line, right? Px plus qy plus r equal to 0. Now, why have I taken this circle? Because, well, it's easy. It's a unit circle and it's easier to explain in this way. And see, we also have minus 1 comma 0 as a point, right? We already have a rational point here. Like I already said that the other rational points can be generated given one rational point. Now, finding one rational point on a conic by Legendre theorem is not a very easy problem. So I have considered this conic for example, so that it would be easier for me to explain. So we already have minus 1 comma 0, a rational point on this conic, which is x squared plus y squared equal to 1. Now this is a rational line because p, q and r are rational, and rational line will have infinite rational points. So let us consider a rational point, this one, on this rational line. And we join minus 1 comma 0 and this point. So we get this line ax plus by plus c equal to 0. This is the line joining minus 1 comma 0 and any rational point on this rational line, right? Now you can, you can calculate that for a rational line, if the coefficients are rational, then the slope will also be rational. So a rational line will always have rational slope. Now, we can also deduce from there that ax plus by plus c equal to 0 will be a rational line, because why? This point is rational, this point is rational. So if we find out the slope by the formula y2 minus y1 by x2 minus x1, we will be getting a rational slope. So this line is a rational line. Now, what we have to do is we have to prove that this point on the circle is also rational. So if we prove for one point, then we can use the same algorithm for the other points, and we can prove that there are indeed infinite rational points on the circle. Now, while we geometrically visualize it, we are basically solving this line, right, with this conic. I hope you can see my cursor. It would be easier. So we are solving this line with this conic. And we know that geometrically, when we solve a line with a conic, the solution is the point of intersection of the line and the conic, right? Now, this line is ax plus by plus c equal to 0. Let's move on to the next slide. So yeah, from here we can substitute the value of y and write it in terms of x, right? Ax plus by plus c equal to 0. So from this equation, we can write that y equal to minus ax minus c by b. And then we are putting the value of y in the equation of the unit circle. X square plus y square minus 1 equal to 0. In the place of y square, we are putting this value. So when we are putting this value, the calculation is done in the slide. We will get a quadratic equation in terms of x. This is the quadratic equation in terms of x. Now we know that a quadratic equation will always have two solutions. It has to have two solutions. And we already know one solution for x. See, this is the solution for x, right? Minus 1 here. This is the solution because we are solving this line and this conic. We already have one solution. Now, please note that the coefficients of this quadratic equation are rational. Why? Because a, b, and c are rational. So our quadratic equation with rational coefficients, if one of the root is rational, then the other root has to be rational, because irrational roots for a quadratic equation with rational coefficients will always exist in pairs. So if we already have one rational root, the other root must be rational. So the x coordinate of this point is rational. We proved it. Now, how do we find the y coordinate? We find the y coordinate by again substituting the value of x here. And as a, b, c, and x all are rational, y will also be rational. So this point will have both of its coordinates rational. Similarly, we can find it for any other point. Say we take this point on the line, it is a rational point, and this is already an existing rational point. This point will also be rational in a similar fashion. And this is how we can explain that a line will have infinite rational points, right? So there will be rational points on this conic section, on this circle, one-to-one correspondence with the line. So there will be infinite rational points on this circle. Now let us understand the same thing but in a more easy manner. As I said that we can take any random line px plus qy plus r equal to 0. Here we take y-axis as the line. Why are we taking y-axis here as the example? Because, well, the parameterization becomes easier. The x-coordinate will always be 0 for any point on the y-axis, right? So using the same method that we discussed about in the previous slide, we find out that the value of x is 1 minus t square by 1 plus t square, and the value of y is 2t by 1 plus t square. Now from here we can see that for any rational value of t, we will get a rational value of x and a rational value of y. And we can put infinite rational value in place of t. So we will get infinite pair of x and y, right? So this is for better understanding, and this is a more easy example. Now this thing, I have used a circle to explain it because it would be easier to explain, but it can be done in case of any conic. It can, so a general equation of conic is ax square plus by square plus cxy plus dx plus fy plus g. And we can use the same algorithm, right? We will select a base rational point, say P, and then we will take all lines of rational slope through P, and we can compute the second point of intersection of the line with the conic. And we will be able to prove that there will be infinite rational point in the conic. You know, in case of parabola, hyperbola, ellipse, we can take any conics and it would give the same result. Now, moving on to yet 1 degree higher, moving on to cubic equation in 2 variables. The proof is not so easy. Basically, there is no proof at all. It's still an open problem. Finding out the rational points on a cubic polynomial in 2 variables. It's still an open problem. So rational points on cubic polynomials of 2 variables. So this is the general equation of a cubic curve. It has 10 coefficients. It's a pretty big equation. But the topic of my talk was rational points on conics and elliptic curves. So what basically is elliptic curve? Elliptic curve basically is the cubic curve itself. So any cubic curve with rational coefficients can be transformed into an elliptic curve. So this is the general form of an elliptic curve. Y square equal to x cube plus ax square plus bx plus c. And this is called the Weierstrass normal form. Now, for a cubic polynomial of 2 variables, there can be either 0 rational points, or there can be finite rational points, or there can be infinite number of rational points. And we still do not know, I mean, the problem is still open that which case we are in. It is still unsolved. We do not know how to determine which case we are in. Whether we are in the 0 rational point case, finite rational point case, or infinite rational point case. It's still an open problem. If you are wondering what an elliptic curve looks like, this is the structure of elliptic curves. Now you probably might be wondering why are there 2 pictures of elliptic curves, right? Now, I already said that elliptic curves are basically cubic curves, right? With rational coefficients, so real coefficients. Now we know that cubic polynomials with real coefficients will either have one real solution, or they will have 3 real solutions, because complex solutions will always exist in pair. So case 1 here is for 3 real solution, because see, it's cutting the x-axis at 3 distinct points, and case 2 is for 1 real solution. So that's why there are 2 different graphs of elliptic curves. But this is the general structure of elliptic curves. This is what they look like. The Birch and Swinnerton-Dyer conjecture. So the Clay Mathematical Institute in 2000, they gave out a list of 7 problems, 7 unsolved problems in mathematics, and they offered $1 million for each solution. So these are called the 7 Millennium prize problems. And the Birch and Swinnerton-Dyer conjecture is one of those 7 problems. If the Birch and Swinnerton-Dyer conjecture, BSD conjecture, we can abbreviate it as, if it was true, then we will have a way to find all rational roots of cubic polynomial, and we wouldn't even have to worry about which case we are in, whether we are in the 0 rational point case, finite or infinite rational point case. It would basically solve all our problem. But it is a conjecture, so it can't be proved, it can't be disproved. So if we can prove it, then the problem about cubic polynomials will be solved for good. And last but not the least is the Model's theorem. The Model's theorem states that for a rational elliptic curve, the group of rational points is finitely generated, which means that, as we have discussed earlier, that for a cubic polynomial, there can be either finite, there can be 0, finite, or infinite rational points. So the number of points that would be generating the other rational points, they will always be finite in number. Like we saw in conics that one rational point was generating the other rational points. In case of cubic, one rational point won't generate, then there wouldn't have been a problem at all. A number of rational points will generate the other rational points, right? But this set of rational points called the basis points that will generate the other rational points on the cubic curve will always have a finite cardinality. That's what Mordell's theorem states. So that's basically all about my talk, and these are the references. If you are interested, you can go and see this video on YouTube. It's by Fields Medal winner Professor Manjul Bhargava, and there is also a book on this topic, Rational Points on Elliptic Curve, by Professor Joseph H. Silverman and Professor John Tate. So that's all. If you have any question, you can ask.
Any questions? Okay, so one thing you said in the lecture. So it's a conjecture means it can be proved. Okay, so there till now there is no proof. Okay.
Yes, sir.
Yeah, so it's not that it cannot be proved and cannot be disproved.
Yes, sir.
Yeah. Any questions? No. Okay, so thanks, Sona Jhori.
Thank you, sir.
Okay, thanks.